So this is the large-scale tropical map discussion for Friday, October 18th, 2019. And I have a very small audience today, but we'll be recording for the outside audience as well. I wanted to start with a background on the present sea surface temperature pattern, which is really quite different from what the Climate Prediction Center had been anticipating back over the summer. There'd been a lot of talk of decline of the El Nino signal, and it seems to be re-emerging in the data set. This is the daily satellite sea surface temperature estimate over the globe, and we want to highlight the places that are absolutely warmest. So this area over here near the dateline and just west of the dateline is both absolutely warm and anomalously warm. This is the warmest region around the world, and we've had a lot of intense deep convection going in this area and westerly winds over the last few months, which have been drawing warm water down onto the equator from points off. And we look around the world. The East Pacific next to Mexico has cooled. The Caribbean is cooled relative to recent weeks. There's warming in the Bay of Bengal region. That's a seasonally normal pattern for the temperatures to increase this time of year there. The most active time for tropical cyclones, one of the annual active times for tropical cyclones in that region is November and December, which occurs then because the monsoon during the summer months shears the tropical cyclones out, but also by wind evaporation feedback cools the ocean so that the temperatures aren't quite as high to support the tropical cyclone activity. A major pattern in the Indian Ocean right now, though, is the Indian Ocean dipole, which has absolutely and anomalously warm water in the western basin right now, with absolutely and anomalously cool water over here. The trade winds in this area have been intense in recent months, so blowing in this direction. During the monsoon, they curl around this way, but this time of year, the trade winds remain intense if they are able to produce a substantial amount of upwelled cold water here, and there's anomalously warm water in the western and northwestern Indian Basin. We'll look at the anomaly in a second. This Indian Ocean dipole pattern with warm, cold, only in the fall, northern fall, is associated with heavy rainfall here and dry conditions here. If you had a similar sea surface temperature anomaly pattern, let me show the anomaly just so the context is there. This is the corresponding anomaly pattern showing the warmth in the west and northwest and the cold in the southeastern tropical Indian Ocean. The warm water during the fall is associated with deep convection over here and intensification of winds blowing this way, which upwells the cold water here and enhances the warm water here. But when you come into the spring, the Indian Ocean is climatologically warmer because it's been longer since the large-scale strong winds that occurred during the previous summer monsoon. So when the whole basin is warm, it actually tends to rain where it's coolest because the rain is reducing the incoming solar radiation that would maximize the sea surface temperatures. It's also increasing the winds and evaporation feedbacks and other things. And so during the spring, the rainfall and sea surface temperature are anti-correlated, and during the fall they're correlated. So in this case, we're getting rain here and a break in the rain of the western maritime continent and southeastern Indian Ocean. This is a typical Indian Ocean dipole pattern that we expect to see during El Nino events. And the Climate Prediction Center has suggested that we are in an ENSO neutral condition. Recently, we've had lower sea surface temperature, cold anomalies in the eastern Pacific Basin here, and warm anomalies. This is the Niño 4 region over here near the dateline, in a pattern that's consistent with some past Central Pacific El Nino events. But since Nino 3.4 has been low in recent months, because we base our determination of the presence of ENSO on Nino 3.4 by tradition, people have decided that there is no ENSO going on right now. And they're wrong, because the ENSO dynamics are still going on right here near the dateline. And these warm waters here, anomalously warm waters, might seem like it's not particularly impressive in comparison with warm anomalies in other parts of the world. But when you put this warm anomaly on the average seasonal temperature for this time of year, it makes this area absolutely warmer than anywhere else in the world on the equator. And so this is the region right now that's driving the large-scale flow. This area is also contributing, and it's contributing more than it normally would in the past, because this Indian Ocean dipole structure is the strongest ever observed. So there's been some trending lately in the pattern of the warmest water. So if I start here, and if I go to the right, it brings up they don't come up in exactly the same place, so it's hard to see what I'm demonstrating, but there's been a general evolution toward warmer conditions. This is monthly average, and this is weekly average. And watch where the eastern extent of the warmest water is located. Monthly, weekly. There's a little bit of broadening and intensifying of the warm signal. I'm going to show that same thing now using the sea surface, or using the sea surface and subsurface temperature data from the Tau buoy array. But before we do that, I want to compare where it's raining now, the OLR signal. These are pentad maps. This is these are weekly maps, 18 to 27th September, 20th September to October 7th, 8th of October to 17th of October. So you can see how evolving forward, there's been a pattern of suppressed convection over the Eastern Ocean, Indian Ocean and the Maritime Continent, and enhanced convection in the west. So you can see how there's a correlation between the rainfall and the Indian Ocean dipole sea surface temperature pattern. So it says because it's warm over here this time of the year, it makes it absolutely warm relative to this area, and it's tending to rain here and not rain here. But looking in the Pacific region, there really isn't a lot of convection east of the equator east along the equator in the East Pacific that we would normally think of as an active El Nino event. These are our Tau buoy array temperature cross sections averaged from 2 south to 2 north. The bottom is the anomalous sea surface temperature, and the top is the total sea surface temperature, it's ocean temperature, not sea surface. The warm water, of course, floats on top of the cold water in the deep ocean, and the trade winds pile up the warm water volume in the western basin and generate upwelling here, which are reducing the temperatures in this area climatologically. But the warmest water, this is centered on ending on October 1st, the anomalously warm water was near and just east of the dateline, and it was anomalously cool in the eastern basin. We can come to the recent pentad, and we see that warm anomalies have extended farther to the east. I'm going to toggle back and forth and watch this area right here. So you see in the last few weeks, there's been a dramatic eastward shift in the isotherms, eastward shift in the warm water. Now, the warmest water of the West Pacific hasn't moved much. You'll notice it's pretty static. But all of the isotherms from east of the dateline have been progressing eastward with time. There's two things going on. One is there was a westerly wind burst over the last several weeks in this area, which forced a downwelling oceanic Kelvin wave, which is propagating off to the east. That Kelvin wave is pushing the thermocline down. So the thermocline is this region right here of the strongest vertical temperature gradient in the ocean. So it's where the warm water is floating on the cold, like a layer of oil on water. So this warm water has shifted to the east, and we can see that very clearly in a longitude time diagram. These are both measured from the Tau array, zonal wind anomalies on the left, and sea surface temperature anomalies on the right. So you can see since the spring, there have been a series of westerly wind events. But between August and September, there was a substantial, strong westerly wind event here. And a relaxation of the trade winds to the east by anomalous westerlies here. Now, when there's a period of background easterly wind, the ocean kind of comes into balance gravitationally with that. So you think of the wind stress supporting a mound of water in the western Pacific with lower sea levels in the east. But then when those trade winds relax and are replaced by westerly anomalies, gravity then wins, and all that warm water wants to rush to the east, and the thermocline pulls back down. So you can see that here. Well, it's been cool for a while in the eastern Pacific. It's now, just in the last few days, it's returned to anomalously warm conditions basin-wide. This is a transition, like several in the past, that have initiated redevelopment of El Nino conditions, which then could maintain through the season. On the other hand, if over the next few weeks we don't have additional westerly winds, then these warm anomalies would erode and you would end up with just a brief period of warming like we saw here. So typically there's a combination of short timescale variability and lower frequency variability. The short timescale variability can change the low frequency variability. So a strong westerly wind event that acts for a week to 10 days, say, can be a transition point wherein the ocean adjusts from one state to another. This is why if we want to predict the climate, we have to predict the weather. Or if you want to understand the risk of a shift in climate variability like ENSO, you need to be able to predict properly the statistics of the weather events. Because, you can't predict a westerly wind burst 2 months in advance. But if you can predict the statistics of the westerly wind burst by properly simulating the dynamics, then you can simulate the risk in a large ensemble of a transition event occurring. So we can't tell just by looking at this that the ocean is going into a more broad El Nino condition for the rest of the season, because it could revert. But there is risk, substantial risk now of that occurring, because the warm water has moved now. Here is what it looks like. The winds again on the left, and the right is the subsurface 20-degree isotherm depth. The depth of the 20-degree isotherm, let's go back to one of these cross sections, sits on average kind of in the middle of this thermocline. You can see it right here. It's not exactly right in the middle all the time, all the way across the basin, but the 20-degree isotherm depth often serves as a proxy in analysis tools for the location of the thermocline. So if you can measure a temperature cross-section at depth and find that 20-degree isotherm depth along the equator, you're going to be pretty close to where the thermocline is. So the westerly wind event was here, and you can see now moving eastward from that point is this subduction of the thermocline. It goes along and then dramatically amplifies over here. Now there's a couple of reasons why this kind of amplification occurs. One is that there may be local winds, but it doesn't really look like there's a strong westerly wind event that's growing it there. So why would a wave begin back here, seem relatively weak, and then suddenly grow? Well, the answer lies in the structure of the mean structure of the Pacific temperature cross-section. So the thermocline slopes upward to the east here. You can think of these waves as Kelvin waves as propagating eastward along this thermocline, much like a wave propagating up the shore on a coastline. So gravity wave propagating up a coastline. As the gravity wave propagates up the coastline, you see the wave gains amplitude and then breaks. Well, a Kelvin wave is a couple of thousand kilometers across. It's not going to break like a gravity wave coming in to the shore that you see on the beach. Instead, think of it like it has a movable surface contour that it's propagating along. So what happens is, as the wave comes along, think of it like the shore is moving. It's pushing the shore down instead of the wave emerging and forcing this big thing that curls over the top. This isn't a wave that would force, that a surfer would ride, but certainly if you were on a boat riding in this area, you would feel a current shift. So the current is changing from westward to eastward, or at least moving in the direction of changing from westward to eastward. If you have absolute eastward current in there, the signal is even bigger, and we could say that the wave is actually broken. A breaking Kelvin wave has an eastward current anomaly similar to the eastward phase speed of the wave, and the eastward phase speed of a Kelvin wave is 2 to 3 meters per second. So if you were on the boat when that went by, you would feel the current shift, and you would then, if you're going toward the west, you'd have to fight that current to keep going. That current would be a couple of meters per second at the largest. When this happens along islands there, we have big flooding events where a jet of warm water heading from west to east actually flows over the tops of some of these shallow or low-lying islands. So they typically form like that during advancement towards stronger El Nino events. So we've got a rapid adjustment going on in sea surface temperature. We can't be sure how long it's going to last, but I'll show you some model runs suggesting potential outcomes going forward. So this is the global satellite map for long wave radiation. So we can see where it's raining right now. It's a region of active rainfall around here. It's not as active as it has been recently. This is a quiet time subseasonally for this area, even though there's a low frequency active convective signal here. There really isn't much convection along the equator, which you'd expect to see if we had a strong El Nino condition in place. But we've had a lot of rainfall recently in the North Pacific ITCZ. The big picture for subseasonal variability right now is active convection in this region. Now, part of it is the Indian Ocean dipole, and part of it is an Indian Ocean active MJO event that's been developing. Let's see here. I've got to get the right figure up. So this is longitude by time in CFS analysis fields, OLR, and up here is the CFS forecast. I use the CFS not because it's a particularly good model, but because there's so much data available that you can do really great statistics on its error functions. This website here is produced by my former student Kyle McCritchie, who's now working at the Climate Prediction Center. Now, we have the two regions of active convection going right now, one over the Indian Ocean, one over the Central Pacific. And there is a circulation signal that's coming around associated with this thing. We're going to look at it in terms of the upper tropospheric flow first. So this is the 200 millibar zonal wind anomaly average across the equator. We see this surge of easterly wind propagating around the world, followed by westerlies. The easterlies form both by the action of Kelvin waves, which have easterly wind in a trough and westerly wind in a ridge, but also from Rossby ridges forced onto the equator in the western hemisphere. Those Rossby ridges forced onto the equator accelerate easterlies on their equatorward sides. So think of as a ridge is moving toward the equator, it undergoes geostrophic adjustment where its amplitude declines as the Coriolis force on the air mass decreases, the air flows outward from the middle of the ridge. And the Coriolis force accelerates that then in the direction depending on the hemisphere. So in this case, it accelerates easterlies along the equator as a ridge is coming from the north and from the south. And I'll show those patterns in the geopotential height anomalies a little bit later. So that is how the MJO circulation signal, this is MJO right here, upper tropospheric easterly wind moving eastward around the world, comes back around, back to the Indian Ocean again, and ultimately arrives back over the Pacific Ocean. But it's occurring at the same time that there's an amplification of the low-frequency background state. The low-frequency background state is the Indian Ocean dipole here, and amplifying El Nino here. The amplifying El Nino condition forces subsidence in the Amazon region, and upper tropospheric easterly wind over the central and eastern Pacific. What's actually happening here is the convection, which you can see right here, coupled to the El Nino signal, is forcing mass poleward. So it's building subtropical ridges to its north and south, but those subtropical ridges get advected eastward by the background westerly wind, and then they produce, on their return side, on the equatorward side, they produce these, let's see, get in there. They produce these low-frequency easterly wind signals here. So this is the return flow on the equatorward side of the subtropical ridge response to the central Pacific convection. So it turns out that where the convection is located, right here, you actually have this counterintuitive convection right here where the negative OLR anomalies are occurring, and westerlies and easterlies. Think about what this means. There's confluence going on along the equator in the zonal flow. But there's mass divergence, net mass divergence because of the meridional outflow from the convection. So we've got a superposition of the MJO coming around and amplification of low-frequency conditions in the Indian Ocean dipole and ENSO. The Indian Ocean dipole signal is likely to break down. It breaks down every year across November through December. This is a seasonal adjustment of the mean state that makes it so the Indian Ocean dipole can't easily perpetuate itself with a positive relationship with convection. So Indian Ocean dipole breaks down first across this winter, but El Nino could keep going for longer, could keep going into the spring or even into the summer, depending on the weather events that interact with it, that could at some point produce a surge in the trade winds that undoes the effect of the El Nino amplification. The low-level wind we need to look at, let's go over to 850 here. We'll get it. There we go. So here's the recent MJO event. Low-level westerly wind anomaly comes around the world. There seems to be two of them. Here's one. Here's another. Comes back to the Indian Ocean. But as it propagates into this region where the Indian Ocean dipole is so strong, MJO convection cannot maintain over the eastern Indian Ocean and the maritime continent. So the circulation then translates the convective signal across. Let's go back to the convection again. The convection comes here. It hops across via the atmospheric circulation and reforms over the western Pacific. So at some point after the turn of the month, given that MJO signal coming around the world, it's probable that we get reinitiation of strong westerly winds again near the dateline. And that poses risk of tropical cyclone development at low latitudes in that region. That would then most likely move westward. The northern hemisphere still dominates this time of the year. they would move westward across the Philippines into the South China Sea area. On some occasions, you do get recurving cyclones still this time of the year. Recurving cyclones are more common in October than they are in November. So coming later on into November, the chances of recurving cyclones goes down. That doesn't mean that they can't happen. It just means that they're statistically less likely. And so when an MJO event comes around in November, you can be more confident in a particular outcome not being disrupted by the tropical cyclone contributions. Again, there are exceptions. So this is the low-level wind forecast from the ECMWF across here. These are WSI products. We've seen a period of recent low-level westerly wind anomalies over the central and eastern Pacific. They've clustered in these groups that have moved eastward. You can see, like right in here, you can see an easterly wind signal. This is the easterly phase of a Kelvin wave, atmospheric Kelvin wave, not an oceanic Kelvin wave. This signal right here is the superposition of the MJO coming this way and the Indian Ocean dipole, where back in September the Indian Ocean dipole signal was fairly weak, but then strengthening of the warm western Indian Ocean and strong convection there intensifies the easterly winds across the Indian Ocean towards Africa, or towards the western Indian Ocean, where the convection is occurring. This is the most intense signal that I've ever seen in the Indian Ocean dipole circulation pattern. It's also the strongest that's ever been observed in the sea surface temperature pattern. But look at what the model does with this. The ECMWF going forward into week 2 starts to break down the intensity of that signal. I think that this is more a consequence of the low-level westerly phase of the MJO cutting across it at that time, instead of actual loss of the IOD pattern. So we got a superposition of a low-frequency signal and a subseasonal one. I do anticipate, though, that the Indian Ocean dipole breaks down as it normally does sometime between November and December. Looking at the upper tropospheric wind pattern, this is the total wind. We're looking at just the last couple of pentads, and we're seeing something that's quite unusual in what people might call an ENSO neutral condition. Again, I don't think that neutral is a good label for this event anyway, but this time of the year, mean westerlies start to extend from the northern hemisphere all the way down to the equator in the climatology. This is the westerly wind duct, which allows for the equatorward propagation of Rossby waves from the middle latitudes. It's like an MJO event over here can produce Rossby waves that come into the middle latitudes like this, and they propagate equatorward, and as they propagate equatorward, the westerlies facilitate that continued propagation. But the anomalous signal now has easterlies across this region. And we're going to look at the anomaly in a moment just to kind of get an idea how and what's going on. It's typical to have a region of easterly wind anomalies come around the world during the western hemisphere phases of the MJO and when the MJO is beginning over the Indian Ocean. And that's kind of what we're seeing here. I'm going to come back to the anomaly and so we can see what's actually going on. The easterly anomalies in this region are driven by ridge anomalies in the northern and the southern hemispheres. And there's a bit of synoptic noise going on in here, but maybe you can see it even better right here. So there's a synoptic wave train. It's coming toward the equator in both hemispheres. And as the waves break onto the equator, they accelerate the easterly wind right here. Now, if the background conditions were suitable for deep convection here thermodynamically, if the ocean surface temperatures were high enough and there were enough available Cape or moisture and so forth, you would end up with a convectively coupled signal going on in here. But these ridges approaching the equator accelerate the easterlies, but they also force divergence of mass on the western side of these easterlies. Thermodynamically, that produces ascent, cools the atmosphere, and generates a relative trough anomaly on the west side of the two ridges. That you end up with a trough anomaly co-located with the easterlies, and that forms a Kelvin wave that propagates to the east, and that moves the signal from the extratropics then along the equator toward the Indian Ocean. So we're looking at this on a small scale here, but there's also a very large scale pattern of twin ridges in here. So if you could break this down by wave number components, you would see planetary scale ridges here approaching the equator from the East Pacific across to the far western Indian Ocean. And then you see kind of the opposite signal with upper tropospheric westerlies on this side. That sets up a pattern of mass divergence here, which reduces the temperature of the profile of all the way through the deep troposphere, and that reduces the convective inhibition at the top of the boundary layer and allows the Indian Ocean convection to begin to organize. Trouble is that with the Indian Ocean dipole pattern in place, with cold water here and large-scale support for low-level easterly wind here, this upper level again, but with low-level easterly wind here across the whole basin and an inability for the wind to actually switch sign in the total sense, so we don't get a strong organized Indian Ocean MJO event. Instead, what happens is the signal comes to the Indian Ocean, propagates across via dry wave dynamics and advection of momentum in the jet. You'll see right here we have a region of easterlies and a region of westerlies along the mean subtropical jet latitude. The background wind here advects these westerlies to the east and these easterlies to the east, resulting in mass transport by geostrophic adjustment into the tropics where the westerlies are accelerating and out of the tropics where the easterlies are accelerating. Eventually, when that pattern reaches an area that supports deep convection, you'll get it to begin, and that's what this model is showing. See right here, deep convection gets going over the Pacific as that signal gets here over the end of the next 2 weeks. So we see similar signals in both the CFS and the ECMWF. Okay, so now this is the Wheeler and Hendon RMM index. You're familiar with the index?
No.
Okay, so the basic idea is that you have two orthogonal patterns. The pattern is say active convection over the western Indian Ocean, suppressed convection over the West Pacific, and then a second pattern that's shifted like a sine wave relative to a cosine wave, so 90 degrees of phase shifted from it. And so you can project the data using low-level wind, upper-level wind, and outgoing long-wave radiation data. You can project the data onto these structures, and it tells you where the large-scale active convection and wind patterns are located associated with the MJO in the present condition. So like if RMM1 is one principal component, it's one time series associated with that pattern, while RMM2 is another time series shifted from the first one in both time and space. When RMM1 is strong and RMM2 is negative, so when RMM1 is positive and RMM2 is negative, the superposition of the two is like you have an Eastern Indian Ocean or a Western Maritime Continent convective signal. So when these two indexes go around, each time step you've got a different estimate of where the signal is centered. So each one of these dots represents a day of data. And this is the history, recent history, where it's just moving around a little bit, wandering a lot. It's spent a lot of time over the Western Hemisphere recently. That's because the index doesn't just trace the MJO, it traces low-frequency variability like the Indian Ocean dipole as well, and so we try to subtract that out, but the way they subtract it out is by taking a 120-day time mean. But if the signal has come up really recently, grown rapidly in recent months, then 120 days average isn't going to take it out, because most of that 120 days the signal was absent and it's just very recently emerged. But you go forward here, the green, this is going forward in time, so this would be like tomorrow, the next day, going forward. In this case, this model, this is ECMWF. This is ECMWF ensembles, and this is a bias correction on ECMWF ensembles. The bias correction is applied to the data fields, not to the index. So if I go to ECMWF here, it's been suggesting for several days, you can't see it on here, but I just follow this every day basically. It's been suggesting an escape where the signal has been stuck over here, but finally it takes off and it heads, within about 2 weeks, it goes back to the West Pacific. But each model run has been suggesting that for the last several days and it hasn't evolved. The models just are not very good at predicting the large-scale evolution of the MJO. Which is kind of astonishing if you think about it, because it's such a big component of the flow and the organized rainfall, and we just don't simulate it very well. But oftentimes when models suggest that the signal is going to break out, it might not break out immediately, but ultimately it does move in that direction. And there's a lot of signal that seems to suggest that the movement of this thing is going to be back toward the Pacific again. That's what this solution is showing, where you get this big convective emergence in early November over the Western Pacific. So I mentioned that the Eastern Indian Ocean and the Western Maritime Continent are not hospitable for deep convection right now because of the Indian Ocean dipole. So when the MJO comes around, it's likely that it weakens in that area, kind of bypasses that area, and then comes back to the Western Pacific and then possibly grows. This is the ECMWF ensembles. They've also got the ECMWF monthly, it's the ECMWF climate model, which integrates forward over a month in this projection instead of just over 2 weeks. You see that like the ECMWF ensembles, this ensemble weakens the signal over the Eastern Indian Ocean. Part of that signal is just that the Indian Ocean dipole is projecting onto the index itself, but it's also because the MJO weakens when it moves into a region where the Indian Ocean dipole doesn't favor it. But look at this. Some of these ensemble members move way out here. This is just one member right here, 3 standard deviations out. If we had an event like this happen in November, the ocean would receive an enormous kick from westerly wind. So the wind stress would produce a strong downwelling Kelvin wave, and we would end up in a stronger El Nino condition as a consequence. But the risk of that happening, at least in terms of this ensemble, is fairly low. Most of the ensemble members are down closer toward they call this the unit circle. This is 1 standard deviation in the index. But at least the pattern suggests that there's some risk of a big MJO event forming. It's maybe a few % of the ensemble. And if you do a bias correction on it, on the data fields, it moves more of the ensemble in the direction of a stronger outcome in the Pacific. This bias correction is based only on recent observations. It's not based on a long-term climatology of the data. If we wanted to do bias correction properly, we would want to know what's the climatology of bias over many years. But the way they estimate it is by looking at recent forecasts. It's insightful, I mean, but it's not always giving you the correct estimate of actual model bias. but it's suggestive that we're likely to have a stronger MJO event come around to the western Pacific in November. If that happens, then ENSO would evolve toward a stronger El Nino event for the course of the rest of the winter. 1986 is a past example of this type of amplification of an El Nino event in the fall in response to a major MJO forcing event. So we've got some models here looking forward over several months. This is what time do we have? Okay, just 10 minutes. So this is the sea surface temperature forecast for monthly data from the ECMWF climate models. The same model we were just showing, but instead of just looking over data for a few weeks, we're looking at an average over a whole month. If I shrink this down a little bit, it makes it harder to see the map, but then we can see what I'm moving across here. So month 0, 1, 2, 3. Watch the sea surface temperature pattern right here along the equator. And watch what this model does. It's got an El Nino pattern that comes out, but then it starts to retract. You notice that it diminishes back into the western Pacific, and we're left come May with a very weak El Nino structure remaining. Keep in mind that in May, a weak warm anomaly constitutes a much stronger impact on the global circulation than a similarly strong anomaly in the middle of the winter, December, January. The reason is that the water is climatologically warm in the spring out here. So add a small warm anomaly to it, the ocean is that much absolutely warmer. But a half a degree warm anomaly in December is trivial because the water is still cold in an absolute sense then. That's the ECMWF, which is suggesting a weaker signal coming around. A lot of that weaker signal is a lack of agreement across the ensemble on how strong the MJO is. And if there's some weak bias or strong bias in its MJO signal, or if ensemble averaging across the ensemble has a whole range of different MJO conditions. Sometimes they may be in the West Pacific, sometimes in the Indian Ocean at a given time. You go out far enough, the ensemble comes out of phase with itself in terms of MJO signals, and so they wash out and you're left with just low frequency averages behind. But in the real world, there would be different levels of risk of El Nino growth or retraction depending on how the MJO actually evolves. This is the comparison to the CFS. It has a much stronger warm anomaly to start with. And you see just gradually over the spring it starts to retract back to the West Pacific. Again, that retraction in the spring doesn't necessarily mean that El Nino is going away at that time, although it often does. What it really means is that the size of warm anomaly that is achievable becomes weaker because the background state, the climatological state, is warmer. And I want to check the weekly data, and this is Thursday, yesterday's ECMWF, and I'm going to blow this up a little bit so we can see it a little bit better, and I think I'm going to change it to geopotential height, departures. So we look at the global response pattern to the forcing signals going on out here as the MJO comes out. This time of year, the response to the West Pacific MJO shifts so that it begins to support a cold signal in the eastern U.S. So you're seeing that in here at the beginning of November, and then a reversal to a warm condition later. You have to keep in mind that the model also has a slow bias. The CFS and the ECMWF both have a slow bias in the propagation of the subseasonal features. So if you want to predict them based on the model, you need to make an operational correction in your mind of the timing of the outcomes to account for that bias. And I'll finally show a statistical model based on my MJO tracking. The recent signal forced by the MJO would have supported a cold eastern United States over the last week and a half, going into the next 2 weeks. But the typhoon event in the Western Pacific produced a large-scale circulation pattern that produced a high-amplitude synoptic signal that propagated across and yielded a warm surge in the middle of what would have been a subseasonal cool signal. So this is what the MJO alone would have looked like for today in the upper tropospheric geopotential height anomaly and the OLR anomalies in the tropics. I'm going to blow this up just a little bit more and then iterate forward. Late October favors the trough into early November, in the eastern United States, I mean. Then it begins to transition. Now it transitions into a pattern that we may not think is particularly common. You end up with wave breaking at high latitudes. It's trying to inject a trough in here, but there's a subtropical wave train as well with a ridge down here. But watch what happens now coming to the end of November. This is as the convection starts to come back to the West Pacific again, the next cycle around, that it builds a big trough event. Now, this is what would happen if the present phase speeds in the signal maintained across the tropics. This signal could occur with different timing because the background wind conditions evolve with the changing El Nino states, and models that try to project these outcomes are going to change the speed of the mid-latitude, the translation of the mid-latitude anomalies, because the models have biased background wind states that evolve with forecast lead time. So a model that has, for example, a weakening subtropical jet stream is going to propagate the response to the MJO across the middle latitude slower, because it's the advection by the westerlies that is the main controlling factor in how fast the mid-latitude signal moves. So if you have a known bias in the background wind speed, you can't just correct for that bias in your forecast by subtracting out the model climatology, which would remove the model bias and just show the anomalous wind, because the subseasonal and synoptic signals superimposed on the model's mean state are advected by the model's mean state and not our mean state, not the real world's mean state. The general suggestion for our outcome in the eastern United States then would be a cool signal at the beginning of November, followed by a warm interruption in the middle, and then in the end of November, amplification of a cold signal again. You can follow also the evolution of the extratropical blocking patterns as well, and their impact on Europe, with cold over Europe in the middle part of November as well, middle to end part of November as well. Major block forming into December. Again, this is timing dependent, but this is the most likely evolution of events if the chronology occurred in the normal order. So it would produce a warm event in mid-December. This is going out so far that I have no confidence in exactly when that would occur, but should the MJO follow a global cycle, this is the pattern you would anticipate. And just one more thing, looking at the low frequency, this is based on low frequency outgoing long wave radiation in the tropics. You've got an El Nino signal kind of developing there. This is based on a 100-day low-pass OLR signal. And so it's not yet diagnosing the Indian Ocean dipole, which it throws a major caveat into interpreting this thing, because we don't really know what's the effect of this big Indian Ocean dipole on the circulation, because that's emerged in less time than 100 days. So it's not producing a strong projection onto this map. So this is based mainly just on the ENSO structure. If you go forward in time into November and December, this is what the El Nino condition this year would favor. There's active rainfall near the dateline, a pair of ridges down here, a wave train develops in this direction. North America doesn't have a strong suggested anomaly, but the North Atlantic does, with a substantial Greenland block suggested in these statistics. And again, if the Indian Ocean dipole contributes something different from this, there's a pretty good chance that at least across November there would be a different outcome than what this suggests by itself. But given just the ENSO forcing, Europe would be likely to have a cold winter of weak wind. So if you're into wind power generation, this is not a good pattern to support the wind market, which would mean that they would be using more natural gas there to keep their power grids up, which then impacts the natural gas market. And so you might choose to make investments in the way that profit from that knowledge. But again, there's a lot of caveats with this time, since the algorithm is not diagnosing the Indian Ocean dipole signal well. Okay, I think that's good for today. Any comments from the room?
No, thank you.
So next week, I have another commitment going on in this hour, so if there is no student presentation the following week, I'll resume again, and I'll announce via email like I usually do. Thank you.